The red dust of Mars holds a monumental question: can we build a self-sustaining city there? From generating breathable air to growing food in alien soil, every aspect is a monumental design puzzle. We'll unveil the ingenious solutions and futuristic structures that are turning the dream of a Martian colony into an engineering reality. The ultimate Martian real estate challenge involves designing habitable structures for humans on Mars, considering the planet's harsh environment, limited resources, and the need for long-term sustainability. Key challenges include shielding from radiation and extreme temperatures, providing breathable air and water, and ensuring a comfortable living space while minimizing reliance on Earth. Transporting construction materials from Earth is impractical due to the vast distance and cost. Settlements will need to rely on in-situ resource utilization, extracting resources like water and minerals from the Martian environment. Building infrastructure like living quarters, research labs, and transportation systems will be essential. This includes developing habitats that can withstand Martian conditions and allow for efficient movement and resource management. Building on a hostile planet presents immense engineering challenges due to extreme atmospheric conditions, radiation exposure, and temperature fluctuations. These factors require innovative solutions for creating habitable environments and protecting structures from damage. Many planets lack a protective atmosphere like Earth's, which provides breathable air, shields from harmful radiation, and regulates temperature. The lack of an ozone layer on some planets allows harmful ultraviolet (UV) radiation to reach the surface, requiring specialized shielding. Utilizing materials with high strength, durability, and radiation resistance for construction. Employing 3D printing technology to construct habitats and infrastructure on-site using local materials. Some planets have scorching surface temperatures due to greenhouse effects or proximity to stars. Global efforts are building toward human arrival on Mars, with NASA targeting a scientific round trip potentially by 2035. SpaceX, under Elon Musk, is also aiming for crewed missions, with potential flights earlier, possibly by 2028, and human missions by 2030. These missions aim to explore the potential for past or present life, understand the planet's geology, and pave the way for future human presence. Missions to Mars present significant technological and logistical challenges. The distance and travel time, 6 to 7 months each way, are major hurdles. Radiation exposure during the long journey is another concern. Ongoing robotic missions like Curiosity and Perseverance are crucial for understanding the planet's environment and habitability. Data from these rovers will inform future human missions. For a Mars mission, self-healing concrete and regolith 3D printing are promising technologies for building habitats. Regolith, the loose surface material on Mars, can be 3D printed into structures using binders like sodium silicate or by leveraging microbial activity to create biomaterials. Self-healing concrete, potentially using bacteria to repair cracks, could also be crucial for long-term structures. Self-healing concrete can incorporate bacteria that, when exposed to water and oxygen, produce calcium carbonate to fill cracks, enhancing the longevity of structures. This technology is particularly relevant for Mars due to the harsh environment and the need for durable, long-lasting habitats. Utilizing in-situ resources like regolith significantly reduces the need to transport materials from Earth, minimizing launch mass and cost. Automated 3D printing with local materials offers a promising path towards autonomous habitat construction on Mars. Protecting against solar flares and cosmic rays, especially in space, is crucial for the safety of astronauts and spacecraft. Shielding, using materials like water or specialized composites, and proper orientation of spacecraft to minimize exposure are key strategies. Earth's magnetic field and atmosphere offer natural protection, but additional measures are needed for space travel. Proper orientation of spacecraft can minimize the surface area exposed to radiation during solar flares and cosmic rays. While the magnetosphere provides good protection, solar wind variations can still cause geomagnetic storms that impact space weather. Proper orientation of spacecraft can minimize the surface area exposed to radiation during solar flares and cosmic rays. Water effective and readily available as a shielding material, though it can be heavy. Pioneering sustainable systems for air, water, and food recycling on Mars involves creating closed-loop life support systems that minimize waste and maximize resource utilization. This includes extracting water from Martian resources, using hydroponics and vertical farming for food production, and employing advanced recycling technologies for air and water. These systems are crucial for establishing self-sustaining human colonies on Mars and reducing reliance on Earth. Techniques like hydroponics and vertical farming in sealed environments allow for food production on Mars, even with limited resources. Close monitoring and management of the interactions between different components of the Martian ecosystem are necessary for long-term stability. Developing innovative recycling and waste management technologies will be crucial for minimizing waste and maximizing resource utilization. Food recycling techniques on Mars and Earth share some similarities, focusing on resource circularity, but also differ due to the unique challenges of space environments. Both leverage waste recycling for plant growth, but Mars requires specialized systems due to its harsher conditions and limited resources. Decomposing organic waste, food scraps, yard waste, into nutrient-rich soil amendment. A key focus is using Martian resources like regolith, soil, water ice, and atmospheric carbon dioxide to create a closed-loop system. Human waste, plant waste, and food waste would be composted and/or processed to create nutrient-rich growing media for plants. These systems aim to recycle water, air, and nutrients within habitats to minimize reliance on Earth. Mars has scarce resources compared to Earth, making ISRU and efficient recycling crucial. Hydroponic farming is a key technology for sustainable life on Mars, offering a way to produce food in the harsh Martian environment with minimal resource use. By growing plants in nutrient-rich water solutions rather than soil, hydroponics can overcome limitations of Martian soil and climate, allowing for efficient food production within closed-loop systems. Hydroponics uses significantly less water, up to 90% less, than traditional agriculture, crucial on a planet where water is scarce and needs to be extracted from the Martian environment. Instead of relying on potentially nutrient-poor Martian soil, hydroponics provides precise control over nutrient delivery, ensuring optimal plant growth. Hydroponic systems can be housed in closed-loop greenhouses, providing a stable, temperature-controlled environment that protects plants from the extreme Martian conditions. For long-duration Mars missions, reliable and sustainable power generation is crucial. Advanced solar, small-scale nuclear, and geothermal energy are all being explored as potential solutions, each with its own advantages and disadvantages. Solar power is a well-understood technology with high potential in certain Martian locations. Solar arrays can be relatively lightweight and compact, making them suitable for early missions. Geothermal energy on Mars requires significant infrastructure development, including drilling and potentially extensive excavation. NASA has limited data on local geothermal availability and has not yet developed the necessary technologies for Mars. Power grids, communication networks, and transportation system for sustainable life on Mars are crucial for overcoming challenges of life on Mars, challenges like dust storms, extreme temperatures and long time delay communication creating challenges of life on Mars. Advanced materials like composite materials and superconducting technologies helping in better conductivity of electricity. Communication systems like satellite and rovers are installed with cameras for real-time data tracking. Drones are used for better surveillance and even cargo transport, particularly in areas with more challenge. The colonization of Mars is the proposed process of establishing permanent human settlements on the planet Mars. Most colonization concepts focus on settling, but colonization is a broader ethical concept, which international space law has limited, and national space programs have avoided, instead focusing on human mission to Mars for exploring the planet. The question of who owns Mars and how it should be governed presents complex ethical and governance challenges, as current international space law lacks specific provisions for resource extraction and territorial claims on other planets. While the Outer Space Treaty declares space and celestial bodies as the province of all mankind, it doesn't explicitly address commercial exploitation of resources. This leaves a legal vacuum that needs to be addressed as human ambitions expand beyond Earth. Ultimately, the vision for Mars is multifaceted, encompassing both scientific discovery and the potential for human expansion into the solar system. Developing the necessary technologies for long-duration space travel, radiation protection, and in-situ resource utilization is crucial. Scientists aim to determine if Mars ever harbored life and if it could potentially support life in the future. This involves studying the planet's geology, atmosphere, and potential water sources.